For some of our core devices in the infrastructure, like router interfaces and some servers, it's very likely we're going to use some statically configured IP addresses. And for the hundreds or thousands of other devices that also need IP addresses, we have a few tricks up our sleeve in delivering those addresses to those devices, with the primary tool for doing that being DHCP, the Dynamic Host Configuration Protocol. So let's use this network topology right here. Here we have our corporate headquarters, and let's focus on one VLAN at the company with an IP network address base of 10.1.0 associated with this one VLAN. We can configure on that local network a DHCP server, which can stand at the ready so that when computer 1 or computer 2 or other devices, when they ask for an IP address, the server can respond and those devices can dynamically be assigned IP addresses. Now, to pull off this DHCP magic, we need a few things configured and set up on the server. The first of which is we need to define a pool, oftentimes called a scope, of IP addresses that the server can hand out to clients that ask for or request an IP address. So in this example, we could train the DHCP server that the scope or pool is the 10.1.0 network. However, because we might have a few addresses that we've statically configured elsewhere in that network, we don't want the server to hand out all the possible IP addresses. So we could set up IP exclusions. So here in our topology, we could say that off limits are .1 through .50. And those would be examples of exclusions where the server would know, okay, I'm handing out IP addresses from this network address space, but I'm not going to hand out .1 through .50. Now, there are situations where we want to have a specific device have the same IP address every single time and still use DHCP to assign that IP address. Well, we can do a reservation that basically reserves a specific IP address based on a certain MAC address. So that can be programmed into the DHCP server, and then when that client, let's imagine this printer, asks for an IP address, the DHCP server says, oh, I see the MAC address you're coming in from is such, and as a result, I've got a specific IP address just for you that was configured as a reservation. And since the DHCP server is handing out address information, we can also, in that same exchange, we can hand out other information that the PC might need. Those would be referred to as options. And some great examples of options that we can hand out to a client. Let's imagine that computer 2 is acting as a DHCP client. As part of the address assignment, some of the options could include, hey, Mr. Computer 2, your default gateway is that guy, Mr. Router 1. And there's different option numbers. So the default gateway information, for example, is option number 3. And computer 2 also may need to know about which DNS server to use. So that could be another option. And that's option 6. And the actual option numbers aren't so critical to remember, but more importantly, the concept that we're handing out additional information, such as a default router, a DNS server to use, the lease time, for example, how long can computer 2 use the IP address that's been assigned, which is option 51. So if we assign a lease time of 8 days, that means computer 2 at the end of 8 days is going to realize that he's out of luck. And that's why most computer operating systems that are doing DHCP leases are going to be renewing them well before the lease ever expires. And other options could include information such as the domain name or the TTL. TTL is an acronym for time to live, because when a PC sends a packet out over the network, in the IP header it includes a TTL. Let's say it's 255, or let's say it's 64. Whatever that number is, TTL inside of an IP header is one way that routers can help avoid a loop, because the TTL, every time it crosses the router in the packet, will be decremented, and eventually the TTL is going to go down to 0. So long story short, we can also hand out the TTL value that a computer should use with its IP address when it sends packets as an option as part of the DHCP process. And the initial communication for DHCP between a client and a DHCP server is 4 packets. The first one is a discover, which is the client trying to discover if there's any DHCP servers. And then a server hearing a discover will offer an IP address back to the client. So inside that offer, it'll have the options and the IP address. And the client receiving that offer says, whoa, fantastic, I'll take it. And that's the request going back from the client to the server. And the server follows up with a final acknowledgement to confirm to the client that yes, he can use that IP address and life is good. And one way to remember those 4 packets is with the acronym DORA, like Dora the Explorer. And in the event that a client issues a discover message and there's no local DHCP server on that local network, it'll go ahead and use an IP address from the automatic private IP address assignment space, which implies that DHCP failed. And instead of having to have a DHCP server local on every single network segment, companies can have a DHCP server that's not local to the network segment where the clients are, if they use a feature called a DHCP relay, or in some vendors they call it the IP helper, and here's what it does. If we enabled the IP helper or DHCP relay function right here on this router, then when the client does its discover message, the router, who's been trained to listen for those DHCP discover messages, can take that and then forward that over the network over to the DHCP server. So for a moment, we're going to double purpose this guy. We're going to make him a DHCP server, at which point the DHCP server can respond back to the router, who then responds back to the client. So the client is still going through the full exchange with the DHCP server, and that DHCP relay or IP helper function is allowing a non-local DHCP server to hand out IP addresses and options to a client, even though the DHCP server is not directly connected to that same subnet. Thought it would be fun to reinforce the concept of how DHCP operates by having a client and server go through a DHCP process and then looking at that exchange of packets through the eyes of a protocol analyzer. So here in this topology, we'll go ahead and we'll pick computer 1 as the DHCP client, and we have a DHCP server local on the network. And on a computer, depending on the flavor of the operating system, there's usually an option of some type to say get an IP address automatically, which behind the scenes means use DHCP. At which point the client will issue a discover message, the server will respond back with an offer, the client will say that's great, it'll send a request message saying I'd love that IP address and the options that you just sent, please let me use them, and the server will send back an acknowledgement back to the client to confirm to the client that it can use that IP address. So we'll be able to see the DORA process, those 4 packets involved in the packet capture. So we'll leverage Wireshark as the protocol analyzer to look at the exchange. Here are the 4 packets in the DHCP exchange, starting with the client and then going back and forth between the client and the server. So with this first entry selected, if we open up the payload, and by the way, Bootstrap protocol is the precursor to the formal protocol that we know and love as DHCP. And if we peek at the layer 3 information, because the PC does not yet have an IP address, there is 0000 for the source IP address in the layer 3 header. And the destination is the layer 3 broadcast address, which gets turned into at layer 2 a layer 2 broadcast. And the switch, when it sees a layer 2 broadcast, is going to forward that to all other ports associated with that same VLAN. So this DHCP discover message basically indicates that the PC who sent this would very much love to find a DHCP server. And it just so happens that in the next entry here, we have the DHCP offer. And let me scroll up a little bit in this output down below. So in this offer, it's offering the IP address of 10.1.0.51 that the client can use. And if we expanded the other options here, it would also include information on the default gateway that the PC should use, the DNS server that the PC should use, how long the lease is good for. And then when the client receives that, it's so happy about that. In the third packet, it has the DHCP request, which is telling the server, hey, you know that offer you just made me? I love it, I'll take it. And then the final packet, going from the server back to the client, is the acknowledgement. That effectively acknowledges all the details regarding that IP address and the options, and also confirms to the client that it's free to go ahead and use this IP address for its communications on the IP network. I'd like you to imagine that we're at a book signing or some other event and we meet somebody and we start chatting and we build some rapport, things are going great, and we discover their name is Mark. And Mark happens to be like the CEO of this huge corporation. We recognize his tower on the skyline. And while we're talking, we realize, hey, you know what? I know a guy named Bob who works in engineering at your company. And if we ask the CEO the question, hey, how do I reach Bob, who works in engineering at your company, it's very likely that the CEO may not have that direct information on hand. But he could refer us to perhaps the VP of engineering, either because the CEO didn't know or he was just trying to get rid of us. In any case, if we take the information for the VP of engineering and we contact that person, and we ask the same question, hey, how do I reach Bob, who works in engineering? The VP may not know that directly either, but may be able to refer us to a manager of engineering who works closer with Bob. And if we did one more iteration and we go to that manager and we asked about Bob, that manager could then feed us the information, for example, the information of how to reach Bob or what Bob's address is. Now, the reason we can use that analogy is because it's very similar to how a computer resolves an IP address associated with the name. So for our example, let's imagine that the person at this PC is running a browser and they want to reach www.cbtnuggets.com. So they type that in, and in the background, their PC needs to translate or figure out what the IP address is associated with www.cbtnuggets.com. So to do that, it's going to send a DNS request over to a DNS server. Now initially, this DNS server may not know the answer to that question, but what it can do, it can go up to the root servers and ask the question. Now the root servers don't know the whole internet, but what they do know is the top level domains. So they know about name servers for .com and .org and .mil and .gov and .edu and so forth. So when this server makes his request to the root, it's sort of like us asking the CEO about detailed information about Bob, who works in engineering. And very similar to how we got referred down to somebody closer to the situation, the root servers can refer us and give us the information about a server handling .com. So for our next query, we can query a name server who's responsible for .com. And when they respond back to us, they're going to refer us to some name servers that are responsible for cbtnuggets.com. So then we make the request again, and then we can get the answer back that says, hey, to get to that website, www.cbtnuggets.com, the IP address is whatever it is. And at that point, the DNS server can cache all that information that's learned from its queries, feed the response back to the client who says, thanks. And with that IP address, it can make its request straight to the IP address that's associated with www.cbtnuggets.com. And instead of having to do all of that over again, the DNS server and the PC are going to be caching that learned information for a period of time at least, so that if they're going to those same sites again in the near future, they don't have to do the separate DNS request again to relearn the IP address associated with the names. And that, my friend, is a high-level overview of how DNS, domain name system, is used behind the scenes to resolve names like www.cbtnuggets.com to an IP address that our computer can then use to reach that site. In this, I'd like to chat with you a little bit more about some of the options that we have with DNS, as well as some of the records and information that are stored in DNS. So leveraging this topology, let's imagine we have a user, and let's pick on computer 1 right here. So we have a user sitting at computer 1. Let's say that user is Bob, and Bob is going out to a website. So Bob opens the browser, types in a URL, and presses enter, and hopes for the best. Now, behind the scenes, Bob's computer needs to figure out, or technically call it resolve, the actual IP address that's associated with the name that he's trying to go to. And Bob's computer has very likely been configured to use a DNS server for just that purpose. Now, the DNS server could be an internal DNS server right here, or it could be an external DNS server out at a service provider or on the internet. Google has a whole bunch of them out there at 8.8.8.8. Thank you, Google. So it could be internal or external. And if Bob makes a request to an internal DNS server, the internal DNS server could actually forward a request out to an external DNS server, who could then go ahead and walk the hierarchy of the DNS tree, starting from the root, if need be, to the top level domain name servers, down to the domain servers that are responsible for the information regarding the IP address of the website that Bob's trying to go to. And when Bob's computer is trying to resolve a name to an IP address, that's referred to as a forward lookup. An example, we're trying to go to acme.com, and the DNS responds back that acme.com is at 23.something.something.something, whatever the IP address is associated with acme.com. And that leads me to the next option, and that is a reverse lookup. And a reverse lookup is when, let me put a little dividing line, a reverse lookup is like when we have a number, like 23.4.6.something, and we're asking DNS, what is the associated name associated with the IP address? So we provide the IP address, and then it comes back and it says it's acme.com or whatever the response is. And if we wanted to have our own DNS server that the public access, we could put a DNS server on our DMZ and allow the firewall to have traffic go to and from that service. Or if we didn't want to house that internally, we could also have a cloud provider that's acting as the home for the DNS server that we're managing. So lots of options. House it locally, house it in the cloud, have a third party do it, and we can forward requests and replicate when needed the DNS records based on where the DNS servers are set up and who's maintaining those servers. And a common term that we're often going to hear with DNS is the concept of a zone. And when we hear the word zone, think of a group. For example, there's a group of records all about acme.com, and that would be in a zone that contains the information about acme.com. So we could have a zone that includes forward lookup information as well as reverse lookup information. And when we're retrieving information regarding DNS, that information is stored in the form of records in the zones that are being kept by the DNS servers. It's important to be aware that there's several different record types. One of the more common ones is right here. It's an A record. That's simply mapping a name like dc-nug.nuggetlab.com to an IP version 4 address. Or if we're doing a query and looking for the IPv6 address of a host, that would be retrieved from a quad A record. An example would be server1.acme.com and the associated IPv6 address associated with that server. And we may have servers that are doing multiple functions. Maybe they're doing web services and file services and other resources that are available. So one common record that's created is a CNAME, a canonical name record. It's really just an alias. So if we had a server at dc-nug.nuggetlab.com that could be resolved to this IP address right here, we could also set up an alias to make it look like ftp.nuggetlab.com. And that's all done behind the scenes so that the customer can actually reach the destination they intended to reach. If we're looking for a name server, for example, we're looking for an authoritative name server that's responsible for all the IP addresses associated with cbtnuggets.com, we could do a request for a name server specifically, and as a result, we could receive an answer that tells us who that name server is. If we're doing reverse lookups, where we offer an IP address and we want to know the name behind it, that's done through the magic of a pointer record, a PTR record. An MX record is specifically for mail exchange. So an email server that's trying to forward mail to a specific domain is looking for another email server. So it'd be requesting an MX record so it can know who to forward to. So if it got the answer of smtp.nuggetlab.com, it would further in the background resolve that name over to the IP address associated with that name, so it could once again know where to forward the packet or to establish a TCP session for the benefit of forwarding email. We also have SRV or service records that can provide additional information regarding services and protocols. There's also several varieties of text records as well, including SPF and DKIM. SPF is an acronym for Sender Policy Framework. It's a way to help identify the legitimate servers that are the authentic servers that can be trusted. And we've had to come up with a lot of creative stuff over the past decade or two because there's so many attacks that leverage how weak sometimes DNS can be that we're doing additional things to help protect the DNS integrity so that it can't be spoofed or at least can't be tricked as easily. Another text record option could be DKIM, which will allow us to include public keys as part of cryptography for once again protecting our DNS information. And then an SOA record, a start of authority record, has details regarding a zone, a DNS zone, including who the authoritative servers are for that zone, how long that information should be cached that's retrieved from that zone, as well as some other details regarding that zone. To help reinforce the concept of DNS and the different types of records, I wanted to go through a couple of examples with you and then take a close look with the protocol analyzer at what some of those requests look like, as well as the response coming back from DNS servers. So in this topology, this is the 192.168.1 network, and I've got an internal server that's acting as a DNS server at .100, and I've got a Windows client at .120. And let's do this. Let's do a few query types from computer 2 that'll go over to the DNS server, and if the DNS server doesn't have that information cached, it'll go out to its DNS server or servers on the internet, which at that point it'll cache it and then feed it back to the client. So we'll make our queries from computer 2, and then as far as a packet capture, we'll go ahead and capture the traffic for protocol analysis on the network connection between the server and the switch. So here on the Windows client at .100, I'm going to issue these commands, and here's basically what they do. I'm going to clear the local cache on this computer. NSLOOKUP is a DNS tool that can be used to retrieve information. This will do an NSLOOKUP regarding www.google.com, and then I'll continue to run NSLOOKUP, and I'm going to ask for different types of records. An A record for an IPv4 address, a quad A record for an IPv6 address, a name server record for this domain. We'll ask for a pointer records, a mail exchange record, a service record, a start of authority record for Amazon.com, and a text record for Microsoft.com. And then I'll follow up with 3 simple name resolution requests. So these are PowerShell commands to resolve Cisco.com, Amazon.com, and www.amazon.com. And if you have a Windows 10 computer, you can do these commands on your own, and I would encourage you. And then take some time to look at the results that are coming back dynamically through DNS on your local computer. So having launched all those, if we go to the packet capture, so this is a DNS query. We're looking for a pointer record. It's also down here in the details regarding what we're looking for. So at the layer 3 information, we have the source IP address of where this request came from. This is the request coming from the Windows computer going to our local DNS server, using a UDP source port of this and the well-known port of 53 going to the DNS server. Now in Wireshark, it's showing us right here that the response to this request is in packet number 74. So if we go to entry 74 And let me go ahead and size this up so we can see everything a little bit more. I'm going to scroll down just a little bit. At the transport layer, the packet came back from the source port of 53 to the client's port of 50,773. And in the DNS payload, it identifies what the original query was, and here's the answer. And the answer regarding that IP address is this host dc-nug.nuggetlab.com. Let's do one other example. Let me go ahead and scroll through here. And let's go ahead and grab this one right here. This is entry 93, which is a query looking for an SOA record, a start of authority record for Amazon.com. It says the response here is in entry 94, so we'll go to 94 for the response. And we'll scroll down just a little bit more. So here is the information regarding our original query regarding an SOA for Amazon.com. And then we have our set of answers starting here and going below. We not only have the name of that server, but we also have the associated A record and IP address associated with that server so that we could reach it in the event we needed to. So if you have any interest in practicing with DNS tools like NSLOOKUP, you can use these commands to do some simple queries against the live internet, and that can help reinforce your understanding of the different record types and the functionality of DNS. I've got a question for you. How important is it for you as a human to know what the accurate time is? And for many people like myself, we want to know what the right time is, and so do our computer systems and network devices. So one technique that we can use to help synchronize time is a protocol just for that called the Network Time Protocol. So here's how it works. We have some authoritative source on what the real time is, and that's usually provided in the United States by a government type of clock that's paying close attention to the Earth's rotations and handling leap seconds when they occur and all that good stuff. So this clock is referred to as being accurate. And then we have servers that are getting the time directly from that clock. We can refer to those as our level 1. They refer to them as a stratum level 1 time source because they're directly tied to the clock. And then these servers at level 2, I'll put a little line between these. These servers at level 2 can get the time from the level 1 servers. And here we use Network Time Protocol to exchange packets so they can synchronize their times. And all the NTP is done based on Coordinated Universal Time, also known as UTC. And the question might come up, well, how does this Network Time Protocol affect my network and our systems? Well, it's very likely that our systems are getting the time from one or more of these servers out on the public internet. So if this is our internal server right here, for example, it could be either going out to one of those servers, or maybe we have our router getting time from one of the servers here. And it may be a stratum or level number 1, 2, or 3. The closer you can get to 1, the more accurate or more precise the time is considered to be. Regardless of which one we use, it's going to be within fractions of a second synchronized with everything else. And so if router 1 was synchronizing with one of these NTP servers, it itself could go ahead and be an NTP server to other devices in our network infrastructure. So we could have other routers or other devices getting time from this guy, or even servers getting time from our internal router. And the idea is to have synchronization of time across our environment. And because NTP serves up the time in UTC, one of the challenges is, what if I'm in the Pacific time zone? How do I deal with that? And the solution is we set our local time zone on devices that we care about regarding local time, and it just does the adjustment based on UTC and what the offset is, whether it's 6 hours or 8 hours or 9.5 hours or whatever it happens to be based on the part of the world that you're in. And that way the computer can be synchronized with UTC and also reflect locally based on the offset for the time zone what your local time is as well. So I thought it would be fun to do a demo, and let's use router 2 as our guinea pig. We'll make router 2 an NTP client, and we'll have him talk to an NTP server to go ahead and learn about the time so he can synchronize its clock. I also thought it would be fun to put a protocol analyzer on the wire to take a look at the NTP packets. And what we'll see is that they are UDP at layer 4, user datagram protocol, and NTP uses the well-known port of UDP port 123. Like the song from Jackson 5, ABC, 1, 2, 3, UDP, you and me. At least that's how I think it might have gone. So let's go to the router interface for router 2 and take a look. So here on router 2, let's start by taking a look at the local clock, the local time, if you will, on this router. And it says that it's currently like 1 a.m.-ish on September 14th, 2019. That's the time on the clock. This is before we're going to synchronize it to a server. Now, we're really going to trust the server because whatever time the server thinks it is, we are going to synchronize our clocks to that. So we're going to configure R2 to use the NTP server at 10.12.0.1. And then we're going to wait a few seconds. And if the clock is way, way off, it may take quite a while for that clock to synchronize. We can use the command show NTP associations just to verify our configuration. And that looks great. We're using 10.12.0.1 as an NTP server. We can do a show NTP status to take a look at our synchronization status. This shows us that the clock is synchronized. Fantastic. And then we'll do a show clock just to verify that the local clock on this router has now synchronized itself to the time on the NTP server. And here in our packet capture, if we look at the initial request from the client, which is here in entry 22, and then we go down, originally it's showing the time of being September 14th, 2019. And then the server responds back with a date that's in 2021. And then they're going to go back and forth, and the client's going to make adjustments to his clock in the attempt to finally synchronize and be on the same page with the server. So if we scroll all the way to the bottom here and take a look at the last server response, we're seeing in this message back from the server that all the timestamps are now for July 4th of 2021, which implies that the client has synchronized its clock as of this packet in the capture to a time that's within milliseconds of the NTP server. And then periodically, the client's going to check with the server just to make sure the time is still synchronized. And if the client finds itself lacking, that it's not in sync, it'll make adjustments again to make sure it's in sync with the server. If you and I have a device on the network that fails, let's say, for example, a printer, and that printer is completely out of service and we're going to replace it, how easy would it be for us to remember what the IP address should be on the new printer so that we can cause as little disruption as possible for our users when putting that new printer on the network? Well, that, my friend, is a challenge that most networks face, and one of the solutions is to use some kind of an IP address management system or software that can allow us to keep track of and have documentation regarding IP addresses that are in use on our networks. As you and I consider all the IP addresses that we might need, we need IP addresses on our firewalls and our routers. Our switches have management interfaces that need an IP address. We can remotely connect to them and administer them. Servers very likely have a permanent IP address, as well as our printers. And then for our clients, we could very likely use Dynamic Host Configuration Protocol to hand out IP addresses and default gateways and the DNS servers that they should use so we can train them dynamically. So we have some devices that we're statically configuring, other devices that we're doing DHCP that might include reservations for some systems. And in keeping track of all those IP addresses, IP address management software systems are really important in big networks. So Microsoft has a product like that that's included as part of the suite of services in Windows Server. And third-party companies such as SolarWinds and other organizations have great applications. And a really effective IPAM system will consider all the sources of information, including DNS and DHCP, and static entries that we can put in as well. So if we had a printer that had to be replaced, whether that printer was getting a DHCP reservation, or whether it was hard-coded and statically configured with an IP address, in any case, if we had an effective IPAM, we could very quickly look up and identify what that IP address should be. And we wouldn't have to go, I wonder what that IP address was, because it'll be documented inside of IPAM. And another reason that IP address management can kind of sneak up on us is because we have a lot of virtual machines also in most of our systems. So if we have 100 virtual machines, they have IP addresses. And we might also have network appliances that are using multiple IP addresses. Here's an example. We might have, between the firewall and our public-facing servers, we might have a load balancer. Or if it has a bunch of features, it could be referred to as an application delivery controller. So if we're providing some type of a web service on our servers, we could have a load balancer with one or more virtual IP addresses that we have in DNS. So that way when a customer is looking for one of our servers, they actually go to the IP address of our load balancer, and then our load balancer will then forward that connection request over to the appropriate server. So with hundreds, or in larger environments, potentially thousands of IP addresses, it's not realistic or practical without the help of an IP address management system to keep track of all those IP addresses. And that's why most large corporations have some type of IP address management system in place. And here's an example of one product that allows us to track, configure, and manage IP addresses in our system.
Thanks for watching our second, and press the button below, like, subscribe, and bell icon.